Welcome to the 10th video on electrostatics for grade 11s. We're going to be looking at energy inside an electric field in this video. Well, in this video we can just do the uniform field. In the next video we're going to do the radial field, inside a radial field. So let's look at what we already know about energy and fields. If I had the Earth over here and I use that as my 0 point, okay, that's 0 meters, and I had a ball of 1 kg which I lifted. So the mass there of that ball is equal to 1 kg, and I lifted this ball to a height of 7 meters above the Earth. I would know, so that's 0 meters and that's 7 meters. We know that the work done on a field is equal to the potential, gravitational potential energy gained by the ball. So let's have a look. The UP, gravitational potential energy, is equal to mgh, mass being 1, gravity we're using as 10 here, 7. So it's 70 joules. Let's look at the work that's done. Well, the work was done exactly against the gravitational field, so there was a force required to move it over a certain distance. The force, we know it's mg, and so it's 1 times 10 times 7 is 70 joules. So we just proved once again, and this is what you already know from grade 10, that the gravitational potential energy gained by an object is due to the work done against the field of gravity, the gravitational force, and it's over a certain height. So the work done is equal to the potential energy gained. Now in an electric field it's exactly the same. Let's have a look at this electric field. We're doing only uniform field at this stage. So I've got a positively charged plate over here and another color, let's use a blue, and I've got a negatively charged plate over here. At this point here I've got a positive point charge Q. They don't give the size, it's not important for this exercise. The thing that we want to look at is what would happen if I moved this positive point charge Q from A to B. So what would happen if I moved it along this path? Well, I would have to exert a force because there's a repulsion between this positive charge and this positive plate. There's a force of repulsion. So I would have to do work to move it to B. And the work that I would do would be equal to the force that I have to apply over this distance from A to B. So let's go to a new page and have a look at that. So we said that the work done is going to equal to the force times the distance that the charge has moved. But we also learned in the last video that force is equal to QE, where that is the size of the charge causing the field, and E is the electric field strength. So what I can do right now is I can substitute QE into F's place over there. So let's just do it. QES. So the work done on an object is equal to the charge, the size of the magnitude of the charge causing the field, multiplied by the electric field strength and the distance that charge has moved. And we know that W is equal to the potential energy, so therefore UP is equal to QES in a uniform field. Let's just go to back to this drawing, and I'm going to ask the question, what would happen if I now, instead of moving from A to B, I move to C? How much work would be done then? Now you'll learn a little bit more of this when we do components of forces, but last year you learned that if the force is not in the same direction as the distance that the object has moved, then the work there's no work being done. So in other words, if I'm holding a case up 1 meter above the ground and I move to the left, although there's a displacement of the case, the force that's been applied is not in the same direction. It's actually perpendicular, therefore there's no work done. So yeah, there will be work done, but it's at an angle. So the distance that's traveled is the same against the force, because there's less force now needed to move it diagonally, so, and the distance is greater. So you'll find that even in this case, that the potential energy is still equal to Q E S, S being from A to B. The work done from A to C is the exact same as the work done from A to B, even though it's at another angle. And that's because there's less force required, because it's moving diagonally across the field, even though the distance is greater. So we're going to now do forces in a radial field in the next video.